Hello everyone. My project is about examining potential non-informative items in a LSAT section using item response theory. The data used for analysis contains 1,000 dichotomous response patterns of 5 items obtained from the Law School Admissions Test, Section 6. And the data was analyzed preliminarily using the classical test theory. For the passing rate, we can see the 5 items have different percentages of examinees who answered them correctly, which means the items have different difficulty levels. For the discrimination index, it is the difference between two passing rates of the top and the bottom students. And a smaller value of the discrimination index indicates that the item is less able to differentiate examinees at different ability levels because the passing rate does not seem to increase a lot as the ability increases. And from this table, we can see the numbers are not close to each other, which means the 5 items may be different in how sensitive they are to examinees of different ability levels. However, the data was originally fitted using the Rush model that only considers the difficulty, but assumes all items can equally differentiate different examinees. Specifically in the Rush model, as the ability increases, the probability of correctly answering different items increases at an equal rate. So in the plot, we see the 5 trace lines representing 5 items. They are parallel. But this assumption of equal slope may not always hold, as in the last slide, without the first item may be less able to differentiate examinees. And the two-parameter logistic model releases this assumption. It estimates the slopes and allows them to be different. So we have some steeper trace lines like the green one, and we have some flatter trace lines like the yellow one. Sometimes, for an extreme example, we may have a trace line very flat, like this. And for this item, the probability of getting it correct is always around 0.5. And no matter how high or low of the ability. In this case, this item may be a weak indicator of the latent trait and may be removed from the test. So the purpose of this project is to examine if there is any item like this that is non-informative and not relevant with the latent trait. And items like this may be removed from the test. Here is the 2PL model. We have observed data x and 3 parameters to be estimated. Theta I is the ability of examinee I, and beta 1j and beta 2j are parameters for item j. This is the probability of getting a 1 for examinee I on item j. And the probability of getting a 0 in this cell is simply 1 minus this expression. And given the observed data x, we take Pij as the probability for one cell when 1 was observed, and take 1 minus P when 0 was observed. And taking the product of all probabilities across the cells, we can write the likelihood like this. For the parameters to be estimated, we assume they have independent priors. The ability and intercept are assumed to be normally distributed with mean 0, and the slope is assumed to have a log normal prior, which means the log of beta 2j is normally distributed. The log transformation was taken because the slopes are usually positive values around 1, and the log of it can be any real number. The complete conditionals are proportional to the product of likelihood and the prior. MH algorithm was used for estimation, and the MCMC chain has 50,000 iterations. And these are some details for coding. Results. To have acceptance rates around 44%, these numbers were used as the variances for proposal distributions, and the acceptance rates for 1000 thetas are close to 44%. And for the 5 pairs of item parameters, the average acceptance rate is 40%, and the range for the acceptance rate is acceptable. Results for model convergence. From the running mean plots, we can see at the end of the plots, the running means became stable for 1000 ability parameters, 5 item slopes, and 5 item intercepts. And this indicates we have reached a stationary distribution after 50,000 iterations. Another formal diagnostic for model convergence shows that the percentage of rejection is quite low, lower than the alpha value 0.05. So we can conclude no evidence was found for non-convergence. To assess the model data fit, the observed score distribution is shown here. We have 5 items and 6 possible summed scores from 0 to 5. Y is the frequency of each summed score, and the black solid line here is the observed frequency. To get the red lines, we do this. In each iteration after the burn-in, a new data matrix was generated using the current jaw of the parameters, and a frequency distribution was computed. The red dashed line in the middle is the mean of the frequency distributions, and the red dotted lines represent the 95% central posterior intervals. We can see the black solid line lies in the middle of the interval. So the model fits the data well. Another measure of goodness of fit is the odds ratio. It is used to detect if the observed responses for items are conditionally independent of each other given the ability. And since we have 5 items, there are 10 possible pairs for which we can calculate the odds ratios. And the right lines in the 10 plots are observed odds ratios. They lie in the middle, which means the model fits the data well. As for the point estimates, the mean of random draws was taken after burning and thinning, and from the table we can see items have different difficulty levels. And for the slope, even though the third item has a slightly higher value, it is hard to see which trace line is steeper than the other 4, and the assumption of equal slope is reasonable. Those trace lines are not flat. All of them seem to be good indicators of the latent construct, so no problematic items was found. Prior sensitivity analysis. Since we are not interested in the ability parameters, we only consider 3 different sets of priors for the item parameters. These 3 sets of priors differ in the variance. The black ones representing medium variance were used in the previous analysis, and the red ones have smaller variances, so the priors are stronger. The blue ones have larger variances, and the priors are weaker. Results show that the slope is sensitive to the prior. As the variance gets smaller and smaller, the point estimates are getting more influenced by the prior, and the value is closer to the prior mean, which is 1 here. On the other hand, the intercept parameter is robust to the choice of priors. They are almost the same. So if we are interested in the estimate of slopes, we need to be more careful when choosing the prior. But if we are interested in the intercept, the prior do not influence a lot. That's it. Thank you.